Okay, so lecture 8. So we will go on to the lossy image compression. So one of the technique of lossy is scalar quantization. Okay, so what we have done before is just a lossless, okay, where there will be no loss, no distortion, okay, to after you do the decompression. So there will be a few techniques of lossy. What we'll see here is only on the quantization and the transformation. So this is the where you will get, okay, if you use lossy technique. Okay, one of the technique is speed and also JPEG. Okay, so what is good in lossy is where you can get high compression ratio, which is 32:1, means you can compress, okay, up to 32 times, okay, compared to the original. Okay, so if you see here, you will reduce the size of the image, okay, but there will be a distortion, okay, between these two. As long as you can understand what is in the image, so it can consider a good technique. Okay, so in lossy, okay, you will your eye is very good in interpolation. Okay, so that's why the eye can tolerate some distortion. So lossy compression is not necessarily bad. Okay, you have to balance up between the quality and also the compression ratio, okay, by viewing, okay, of our human eye, where we are good in interpolation. So that's why we can tolerate, okay, some distortion in lossy technique. Okay, so in lossy, what is the problem is where you will create a distortion. Okay, if you have a technique, okay, of lossy, so of course there will be a distortion because you already reduce much where the compression ratio is high, so you will not get the same as the original. So for example, this is the model of lossy, where you will encode. Encode means you will compress the image using any of the technique of lossy. Then you will compress the image, which is represent as Y. So after you compress, then you want to get back the original. So you have to do the decoder or decompression, okay? And it will not get as what is in the original. So you will have a distortion. That's why you will get X gap, okay, the decompressed image. So lossy compression, okay, you will not get as the one in the original, okay. So for this reason, you have to measure the distortion. So this distortion commonly used as a mean square error. So you will get the distortion by getting the difference between two images. This is the original, this is the decompressed. So you will calculate the difference between these two, okay, all the pixel in the image, and divide by n. Okay, so that's how you get the MSE. So MSE means the mean square error. So it should be not much. Okay, the value of MSE, if it is big, then it shows there is too much error. Okay, there is too much distortion. So you have to trade off between the quality and also the compression ratio, so that your MSE is not that big. Okay, so after you get the MSE, you will get the peak signal to ratio. So this is one is the standard way to measure the fidelity of the image. Okay, so but PSNR is not everything, so you have to trade off between the distortion and also the compression ratio. Okay, as been shown here by using SFIT. So the more pixel number bit of pixel, the more PSNR will go. Okay, So you have to trade off between the distortion and also the compression. Okay. So next is the quantization. So one of the technique in lossy. Okay. So there will be a problem, okay, using quantization. Why? Okay, because once you quantize your image, okay, so the continuous form, okay, will be represented as a discrete. Okay, our real image is a continuous. So once you digitize, so all these continuous, the signal representation, okay, in computer will be discrete, okay, with finite precision. So that's how the quantization comes, where you will lose some data. So it is not as what in the continuous. So higher precision requires large storage. Okay, if you want to remain, okay, your image as good as the in the real one, then you have to have a high precision. Okay, which means that you will need more number of bits, okay, to represent each of the image. So if it is high, then it will require large storage. Okay, so large storage means you will need more storage, then it will be a problem to transmit and also to save your data. So this is the how the quantization be done. So you will have the analog signal, okay, the one that in real signal, okay, you have to sample and then you will quantize. So this we consider as the analog and digital converter. So once it will convert, okay, or quantize, so it will be in a digital signal. So then you will get the digital signal and then you will get back to the analog. So you have to do the digital analog converter. Okay. So what is quantization? Okay, quantization is a process of representing a large or possible infinite set value with a much smaller set. So as been mentioned before, so if you have a continuous, so you want to represent it as a discrete. Okay, so of course it will lose some information. Okay, if you want to remain or you want the image will be in a quality where you will get the same as the original, so you will need more number of set value. Okay, but quantization, okay, you will represent a large, okay, or possible set of value with a much smaller set. So this we call it as a scala quantization, where you will a map of an image input value x into a finite number of value y. So it can also be a vector quantization where you will encode values for multi-dimensional vector space into a finite set of value, okay, from a discrete subspace of lower dimension. So the design of the quantizer has a significant impact, okay, on the amount of compression obtained and loss incurred. So in lossless compression, so you will have the quantizer where quantizer will do the encoder mapping and decode the mapping. So you will have the encode mapping and decode mapping. So the encoder will divide the range of source into a number of intervals. So each interval is represented by a distinct code word. Okay, so once you encode, then you will decode. So decode will do the same as the encoder. Okay, where you will do the not the same, the vice versa step. So for each received code word, the decoder will generate a reconstruct value. Okay, so once you encode, then you will get the code word. So once you decode, this code word will be reconstruct the what is in the original. So encoder will divide the range of value that the source generate into a number of intervals. So each interval will be mapped to a code word. So it is a many-to-one irreversible mapping. So the code word only identify the interval, not the original value. So code word will represent, okay, a number of intervals. So if the source or sample value comes from an analog, it is called a AD converter. Okay, so to be more understand, so this is how the coder will be done. So you will have a range of bit. Okay, so it depends on the number of bit that your data or your image will be represented. Okay, so once you encode, then this range will be divided into sub-intervals. So the sub-interval then will be, you will have a code word. So means that the range from 0 to negative 1.0 will represent that as 011. Okay, so this is how the encoder will be done. So it will not take, okay, each of this value, okay, between these two. Okay, so the encoder will represent this range as one code word. So for example, you map a 3-bit, okay, digital to analog converter. So this is the input. So once you do the encoder, so this will be the output. So the component of okay. So once you encode, then you will do the decoder. So output of encode, you will have the code word. So this code word, the code decoder give an estimated value that source might be generated. So you will generate, okay, this should be the same as the original. Okay. Usually it is a midpoint of interval, but a more accurate estimate will depend on the distribution of the value in the interval. So usually we will take the midpoint, okay, of that particular interval, so to reconstruct back, okay, the source. Okay, so in estimating the value, the decoder might generate some errors. So this is the error. So the difference between the signal, the input signal and the output. So it can be shown here. Okay, suppose you have a sinusoid for cos 2 pi t was employed every 0.5 second. So the sample was digitized using the AD mapping shown in figure below. So this is the T, okay, the input. So once you apply, okay, on the sinusoid, so this will be the output. So once you do the encode, where you will transform the analog to digital, so this will be the output. So once you have the output, the encoder, the output of the encoder, so then you will reconstruct back to get as what is in the input. Okay, so then you will do the decoder, where you will do the digital to analog form. So you will get this. Okay, so as you see, the output will have different with this. So the two different, okay, we get the difference, we call it as an errors. So this is the errors that will be obtained during you do the quantization. Okay,